I think it's obvious to most people that look from outside looking into the fusion industry. It's pretty obvious we're iterating on the lessons learned for fusion. We're advancing the knowledge of the science of fusion. And while that is important, and it's one that we talk about very often, we should not trivialize the lessons learned in engineering of how to build it, of how to operate it, how to do it safely, how to do it fast, how to get high quality information from it that influence your decision-making ability, to have high quality decisions, do them fast. And to be able to have engineering lessons learned, you have to have operational lessons learned too. So that's sort of the three different things that you get out of rapid iterations of these builds is the expertise in designing, building, and turning those things on, the operational experience of how it performs at the conditions that you planned on based on your simulations and how you built the machine, and then the lessons learned on the science. If you can increase those cycles, you get that institutional knowledge from operating them often, be able to build them, and then learn from the science. That's ideal. That's what we're shooting for.
If you can go small, that allows you to iterate on the machine really quickly and be super capital efficient. You can build multiple machines, you can learn quickly. And so we're trying to bring this like new space approach, rapid iterative test fail fix to fusion.
One of the important things about having a small reactor isn't just your iterations to be able to design it and iterate, make it better. It's also the best way humans have ever found in reducing the cost of something complex is economies of scale or mass manufacturing. And beyond a certain scale, we just don't have the tools available to mass manufacture them. So, basically when we started this off, it was like anything smaller than a Toyota truck is where we want to be scale-wise to be able to enable the tools and processes to have high quality production from a single factory. Even if you crack fusion on a very large power plant, your ability to scale it is going to be severely limited by the supply chain and mobilizing specialized crews to go put it in place there. Conversely, if it's small enough, you can have a gigafactory where you've got all your workforce, they've got their work cells, you've got the controlled environment around it, and you pump these things out and ship them anywhere they want in the world. And then you've got the added benefit of a modularity where you can expand in place, you can take things offline for repairs or maintenance as you need to. That's our vision for fusion, to be able to not only make it possible, but to make it economical.
We want this to look a lot like automotive manufacturing, where you're mass producing these things, building tens of thousands of units a year. That's where we're ultimately going to go. We're about to expand to a second site in Richland, Washington, which is called FusionWorks. That facility is going to be able to host some very capable fusion machines that we can't do in our current lab. And so we're basically just going to be pushing performance higher and higher as we build these fusion machines at higher voltages, higher magnetic fields.